Thanks very much for the introduction, Murray. I hope you guys all got a cup of coffee and some fresh air because we've got a power hour of quantum physics coming up. I am Andrew King, Director of Performance Research at D-Wave, and today I'm going to be talking about coherent quantum annealing. And I'm going to be talking about applications to optimization and applications to simulation of quantum systems. So before talking about quantum annealing, I'm going to give a little bit of an introduction, and I'm going to start with actual thermal annealing, simulated annealing, which is kind of a classical analog of quantum annealing. So in simulated annealing, what we have is a classical Ising Hamiltonian. And those of you who have programmed the D-Wave processors will recognize the H's and the J's in this equation. So this is just a classical energy function that you can use to define NP-hard optimization problems. Okay? And in simulated annealing, what we do is we start at a very high temperature where everything is very random, and then we gradually lower the temperature until we settle into a low energy state. It's a very common, well-used meta-heuristic method for optimization. Now, in the picture on the lower left here, I have an annealing schedule. And I haven't drawn it as a lowering temperature. I've drawn it as a steady temperature and an increasing energy scale of the classical Ising Hamiltonian. And the reason I do this is because it's just equivalent. You can just divide by one or the other. And this is more analogous to what we do in the processor, where the temperature is essentially constant. Now, this is a technology that is actually thousands of years old, and we felt that it could use a bit of an update. So we added quantum fluctuations. So the quantum fluctuations are imparted by a transverse magnetic field. And notice that now I have quantum fluctuations and thermal fluctuations. This is called an open quantum system. I live in Montreal, and it's January, and I'm very happy to be here live in Miami. But at home, when it's January and it's minus 15 Celsius, we don't leave the door open. And just like that, in a quantum system, we don't want to have an exchange of energy with the environment. So when we have thermal fluctuations and quantum fluctuations, this is an open quantum system. And I want to talk about closed quantum systems. So we're going to take the temperature away, and that means that we can basically ignore it. So it doesn't really matter what the temperature is. We don't even have to think about it. We can act like it's not there, the thermal environment. It surrounds us, but we don't exchange energy with it. There's no interaction. So applications of quantum annealing can roughly be split up into two categories, simulation and optimization. And often in simulation, we don't want to simulate classical systems a lot of the time. We want to simulate quantum systems. And to do that, we actually want to read out at the middle of the anneal. So the annealing schedule here, where the quantum fluctuations decay or are attenuated throughout the anneal, these interact with the classical terms and produce really interesting exotic states of matter that we want to simulate. But for optimization, we actually want to go all the way to the end of the anneal, where there's a classical system and a hard optimization problem to solve. So these are the two ways that we're going to use the system. And I'm actually going to talk about a slightly different way. I'm going to talk about simulating quantum systems by annealing all the way to the end. And this is kind of a non-equilibrium dynamics simulation of quantum physics. So one of the inspirations for building these D-Wave quantum annealing processors was a set of experiments done in the late 90s where they took a disordered alloy, so it's actually a chunk of metal, and they put it in an actual magnetic field, not just a term in an equation. And they showed that by attenuating the transverse field, i.e. by annealing the quantum fluctuations, they could actually get to a low energy state of this disordered magnet faster than they could by attenuating thermal fluctuations, i.e. by annealing it. And so in this figure, you've got this phase diagram, and we want to get from this high energy, high randomness paramagnetic phase down into an ordered glassy phase, or a low energy glassy phase. And we don't care how we do it. We want to do it quickly. So the three ways that I've talked about so far are thermal dynamics, which everybody already knows how to do, open quantum dynamics, which we can do pretty easily in D-Wave quantum annealers, and coherent dynamics. And we're going to do that by annealing very fast and by improving the coherence time of the qubits. So I'm going to talk about something that is a lot more simple than a disordered three-dimensional magnet. I'm going to talk about a one-dimensional chain. And the reason that we're going to talk about this is because it has a closed-form solution. Everybody knows exactly how to solve it. OK, a lot of people know exactly how to solve it. And so what you have is just a set of spins, or qubits, in a chain. And so it's a big loop of hundreds or thousands of qubits, one connected to the other, one connected to the one before it and the one after it. This was recently published in Nature Physics in September 2022, and is a collaboration with Sei Suzuki, Daniel Idar, and Hidetoshi Nishimori. So we've got the same annealing schedule as before. Let me just point it out again. We're going to cut down the quantum fluctuations and turn on the classical problem. And notice we don't have a temperature here. We're annealing coherently. So what you go through in the middle of the anneal is called a quantum phase transition. And at the quantum phase transition, there's a macroscopic shift in the characteristics of the magnetic system that we're dealing with. So on one side, at the beginning of the anneal, you've got a disordered quantum paramagnet. And on the other side, you've got a long-range ordered ground state, where all the spins should be up, 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 or down, 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 down in the classical solution. But if you make a very long chain and you go through this fast, then you're actually not going to get all of them up or all of them down. You're going to get up, 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 and then you're going to get a bunch that are down, and then you're going to get a bunch that are up. And at the interface between these domains is something called a kink. So we're going to talk about the statistics of the kinks in this system. So you can see at the bottom left here, we're looking at 4.8 nanosecond anneals and 49 nanosecond anneals. This is pretty fast. And you can see this psi, this is a correlation length, which just tells us, on average, how far apart are the kinks. So here we've got a correlation length of around 15, and here we've got a correlation length of around 47. And you can look at that and say, well, that looks like a factor of about square root of 10, whereas the annealing times differ by about a square root of 10 if you've looked at this a lot. And there's actually a lot of foundational theoretical work called the Kibble-Zurich mechanism that describes exactly what should happen in terms of this scaling. So what we expect to see is an inverse square root scaling of the kink density as a function of the anneal time. So on a log-log plot, that tells us that the kink density should be a straight line. And Mark already showed this plot. This is coherent theory. And you can see the data over here, which I can loosely call the coherent regime, where it falls on top of the coherent theory. It's not just the slope of it that's correct, it's the height of it. And this is one of the really nice things about studying the one-dimensional system. We know exactly what's supposed to happen. So we can just take single qubit measurements, plug them into a known equation from previous studies, and we can determine not only the slope of this line, but also the height of it. So we know exactly what the solution should be in a coherently annealed quantum system, and we can see that our results agree very well. Now this is j equals minus 1.4. That means that we're programming a strong coupling into the chain. And up here you have, well, I actually can't remember what this is. I think this is 0.24. It's quite a lot less. But you can see that this is peeling away much earlier. And so this is one of the parameters that we're going to be improving for Advantage 2, is the energy scale. So the strength of the couplings is going to be increased for Advantage 2, which is going to give us a big win in optimization. Now, another characteristic of coherent annealing is that you can see we've got different temperatures that we're running this experiment at. We start at a minimum temperature of around 10 millikelvin, and we go up to a relatively balmy 30 millikelvin. And you can see in the coherent regime, it doesn't make much of a difference what temperature you're at, because the environment may be warm, but you're not interacting with it. So we get a lot of really good evidence from this reasonably simple plot that tells us that we should have a lot of confidence in coherent annealing and our characterization of this programmable quantum system that we're dealing with. There's a lot more data in the paper, but I'm going to move on now to the more complicated system, which is a lot more like this disordered chunk of metal that I was talking about earlier. And this is a three-dimensional spin glass. So it's a disordered magnetic system. In other words, it's a random optimization problem, depending on whether you're a physicist or a computer scientist. And if you're neither of those, you can just pick whichever one you like better. So this is a collaboration with Anders Sandvik at Boston University, who is an expert in critical phenomena, among other things. And now I'm going to come back to something else that both Mark and Emil talked about earlier, which is embedding. So a simple cubic lattice does not exist in the PEGASUS architecture. So we have to embed it. And that means that we take pairs of qubits and we glue them together with a really strong coupling. So basically, we program a really strong energy penalty that is violated if they have different values. So they act as one unit. And by doing this in pairs, we can program a simple cubic lattice into the system, a very large one on thousands of spins. Now, this is great. This really shows the payoff of expanding connectivity from D-Wave 2000Q to Advantage. But we had to make some compromises to do that. So we compromised in energy scale, and we compromised in the noise profile. And despite these compromises, we can see that D-Wave 2000Q is significantly outperformed by Advantage in these problems. So you can actually get this plot to go a lot further on Advantage, because you can do huge systems on it. But this just shows a systematic scaling advantage in optimization problems of this nature. And the reason is you have to use 4 qubits for a logical spin rather than 2 qubits. So here we've got a big advantage by using Advantage. So enough about that. Let's talk about phase diagrams. In this paper, this is a preprint, and it's available on ARXIV. There's 2 types of systems that we study in this experiment. We study small systems and large systems. So in the 1D system, even if you have 2,000 spins in your 1D chain, because of the Jordan-Wigner transformation, which exploits the structure of the problem, you can solve it no matter how big it is. It's really easy to solve classically. But that's not the case for 3D spin glasses. So we're going to start actually with 16 qubit instances, and these are so small that we can brute force the quantum solution. And that's in figure A. So by brute forcing it, we get the same kind of data that we got for the 1D chain, where we know exactly quantitatively that we're getting what we expect. And there's no fitting parameters in this equation. We're taking single qubit measurements, and we're looking at a brute force classical simulation of this small instance, and we're seeing that we get very, very good agreement in the quantum experiment. Then we blow up the experiment by 100 times or 300 times. We make it up to 5,300 qubits. That's the largest system we simulated. And that's figure B. So this is a 3-dimensional spin glass, and on each of these purple couplings, these lines are couplings. On each of these purple couplings, you assign it to be plus or minus 1 randomly. And on the gold ones, you just split plus or minus 1 across 2 physical couplers. This is like a kind of a buttressing that we do. Just we get it for free. So this makes the embedding more stable. So we've got a simulation. We know that we can embed a 3D lattice. And now we're going to look at the phase diagram. So thermal annealing and quantum annealing, they both get into the spin glass phase. And if you go slowly enough, you can get to really high-quality solutions, which are low-energy solutions of this random optimization problem, or disordered magnet. And you both start thermal annealing and quantum annealing from a very random paramagnetic state with a very small correlation length. But the way that you get into the spin glass phase is completely different. So for thermal annealing, you go through a thermal phase transition. For quantum annealing, you go through a quantum phase transition. And these are governed by different scaling exponents. We can kind of sum up and skip a few of the details and say we're only interested in one scaling exponent. This is called mu. This is the y-axis on the plot on the right-hand side. This is the Kibble-Zurich exponent, and it roughly tells us how fast the dynamics of the solver are. So if you have a fast solver, it has a small mu. If you have a slow solver, it has a large mu. And we compare here 3 dynamics. We compare the dynamics of simulated annealing and quantum annealing. And in the middle, we simulate the dynamics of simulated quantum annealing, which is kind of a classical emulation of a quantum system that doesn't get the dynamics right, but it gets certain equilibrium properties right. And you can see that quantum annealing is fastest. But there's something else that's interesting, and maybe this is going into a bit too much detail, but we can tune the doping, as they say, in these instances. So P is the doping probability with which we set a random coupler to be +1 rather than -1. And if P goes to 1, then the problem is not hard at all. And as you reduce P from 1, you get to a phase transition where the problem becomes hard. And so you can see on the easy side of the phase transition, all of the solvers have the same Kibble-Zurich exponent, basically. It's 2. But on the hard side, where you have hard optimization problems, you have quantum annealing with a very significant advantage over the classical dynamics. And this is exactly what we want to see. We don't use quantum annealing to solve easy problems. We want to solve hard problems with big speed-ups in quantum annealing. So it's really nice to see phenomena like this, where the harder the problem is, the bigger the advantage is. Now, a lot of you don't care about Kibble-Zurich exponents, and that's okay. So I'm going to talk about the scaling of residual energy. And if you don't care about residual energy, you can just think about this as how much money is left on the table in terms of my approximation ratio. So we can go back to our theoretical framework and say, how fast should the residual energy scale as a function of annealing time? So in other words, as we put more and more effort into the computation, how fast does the residual energy decay? And so we have theories for that, or theorems. And so we get these straight lines on the left-hand side plot. And you can see there's a couple of types of deviations. So first of all, quantum annealing and simulated quantum annealing, the slope isn't quite right. And this is kind of explained by the fact that this theorem is for the critical point not deep in the spin glass phase. That's okay, don't worry about it. But also, there's a more obvious deviation from theory, which is at the bottom, quantum annealing is no longer scaling on a straight line. It's got a big hump. And this is kind of very similar and very analogous to what we saw in the 1D chain. And so we're very confident that this is caused by exchange of energy with the environment, i.e. decoherence. And Mark talked a lot about improving the noise profile and improving coherence in the Advantage 2 processor, and also increasing the energy scale. So I personally am really excited to see what this plot is going to look like on Advantage 2. So what we expect to see is that this hump gets driven down into a very low energy regime, and you get a bigger advantage over simulated annealing. Now, I want to point out that this is, as far as I know, the largest programmable quantum simulation that has ever been done. It's on over 5,000 qubits. And so the agreement that we get with theory is quite remarkable. But that's not all. So if you look at the left-hand plot, you can see that I'm not using the same measure for the actual physical experiment and the Monte Carlo simulations. So MCS is a Monte Carlo sweep. I'm just doing that to get all the data in one box. So if you actually compare time versus time, nanoseconds versus nanoseconds, you can see a huge spacing between quantum annealing and the software solvers. So it's about 100,000 times against simulated annealing and about 1 billion times versus simulated quantum annealing. So I have to say we ran the high-performance computing cluster down to the bone for months on end to get all the simulated quantum annealing experiments done. We had no such problem with the quantum annealing experiments. So just to conclude, I've talked about coherent quantum annealing and hopefully convinced you that we can do really interesting things in terms of simulating not only well understood but not very well understood quantum magnetic systems. And the Schrödinger dynamics, here we're realizing programmable Schrödinger dynamics on thousands of qubits. This is totally out of reach of classical methods. So for a 1D chain, it's okay. For a 2D chain, you can exploit the structure a little bit and get up to about 100 qubits. And for 3D, things look pretty hopeless. And right now, one thing that we're working on is quantifying exactly how hopeless things are with the classical solvers. Moreover, when we look at classical optimization, quantum annealing is showing a scaling advantage over the classical dynamics. So this is really encouraging because it's exactly classical optimization that many customers are interested in. So it's always nice when the physics experiment comes out with an example like that. So I just want to say if 5,000 qubits is not big enough for you, then we have an open source hybrid method that can solve larger than chip lattice problems. This is on ARXIV in the bottom link. It can be hybridized in a very straightforward method that's open source, so you can check out the details if you like. And if you feel a little bit overwhelmed by all the details that I've presented, don't worry. This is cutting edge science. We have lots of resources to help out online and accelerate your quantum journey. Go to the URL to view case studies, industry reports, white papers, performance reports, demos, code samples, and more. Now I'm going to pass it off to Alex Kamenev, who is going to talk about iterative quantum optimization. Thank you very much for your time.